Welcome back. In this video, we will be discussing stoichiometric ratios. In previous videos, you learned how to write and balance chemical equations. We will now utilize the coefficients from a balanced equation as a ratio of how reactants are used up and how products are formed. Let's take the following balanced equation as an example. 4NH3 gas reacts with 5O2 gas to form 4NO gas and 6H2O gas. The coefficients tell us that 4 molecules of ammonia will react with 5 molecules of oxygen to form 4 molecules of nitrogen monoxide and 6 molecules of water vapor. Every time this reaction occurs, the ratio of 4 to 5 to 4 to 6 will remain constant. Since samples of these reactants will be in quantities vastly larger than a few molecules of each, it is better to think of the coefficients as moles of each reactant and product rather than as individual molecules. By doing so, we can now refer to the ratio of coefficients simply as the molar ratio. Using the molar ratios from a chemical equation, we can determine how many moles of a given reactant or product will be consumed or formed from an initial sample. For example, if we have a sample that contains 6.4 moles of ammonia, how many moles of oxygen are needed to completely react with it? We can use the coefficients in the chemical equation as a mole ratio conversion factor. This allows us to convert between the ammonia and the oxygen. We have our 6.4 moles of ammonia. We are using our 5 to 4 ratio. So we will use 5 moles of oxygen gas every time we have 4 moles of ammonia. Note that our moles of ammonia will cancel, leaving us with 8.0 moles of oxygen gas. How many moles of water vapor would be formed in this reaction? We again start with our 6.4 moles of ammonia. But this time we have a different coefficient in front of our water vapor. So every time 6 moles of water vapor are formed, we use up 4 moles of our ammonia. Again, our moles of ammonia will cancel, resulting in an answer of 9.6 moles of water vapor. Samples of reactants are rarely measured in moles. Generally, the easiest measurement of a given sample is mass. Fortunately, we learned in a previous video that we can convert the mass of a molecule or compound into moles using its molar mass. Let's try this example. What mass of water vapor is formed when 78.5 grams of oxygen gas is reacted in the presence of excess ammonia? Let's figure out what steps we need to do. First, we have the balanced chemical equation. If you do not already have a balanced chemical equation, this will always be your first step in any stoichiometric calculation. Second, we need to convert the sample's mass into moles. This can be done using oxygen's molar mass. Remember, oxygen is one of our diatomic molecules, therefore its molar mass is 32.00 grams per mole. Third, we need to convert the moles of oxygen into moles of water vapor. We can do this by using the coefficients in the balanced equation as a molar ratio. Our molar ratio is 6 moles of water vapor for every 5 moles of oxygen gas. Finally, we need to convert the moles of water vapor into mass using water's molar mass. The molar mass of water is 18.016 grams per mole. When we put each of these pieces in, please note that our units canceled from grams of oxygen, moles of oxygen, and moles of water, leaving us only with the units of grams of water vapor. Our final answer, remembering sig figs, is 53.0 grams of H2O. So, a 78.5 gram sample of oxygen gas will form 53.0 grams of water vapor in the presence of excess ammonia. We can also calculate the products to the reactants. For example, if 32.7 grams of nitrogen monoxide gas is produced, how many grams of oxygen were consumed? Our steps begin the same way as our previous example. We take our sample size of 32.7 grams of nitrogen monoxide. We must convert our grams into moles using nitrogen monoxide's molar mass. The molar mass of nitrogen monoxide is 30.01 grams per mole. Now we need to convert from nitrogen monoxide into our oxygen gas. Our molar ratio will be 5 moles of oxygen gas are consumed every time 4 moles of nitrogen monoxide are produced. Finally, now that we have moles of oxygen gas, we need to convert that back into mass using its molar mass. Make sure that as you do this, your units that you don't need get canceled, grams of nitrogen monoxide, moles of nitrogen monoxide, and moles of oxygen gas, and you end up with the units that you want in the end, grams of oxygen gas. Again, use your sig fig rules for multiplication and division to complete your final answer of 43.6 grams of oxygen gas.